of aspect of astrophysics, ranging from star clusters to cosmology. And today we will talk about just about one aspect of this research, which is the star cluster. So please welcome him.
Thanks. It's great to be here, especially on this thing today. Okay, let's start with some pretty pictures, just to remind ourselves what we're talking about. Can we see this, or do we want? I guess we don't want it too dark.
I can vary the brightness on
okay, all right. Well, anyway, so let's do the pictures first. This is an old globular cluster in the Milky Way, very typical of about 150 of these types of objects we have in our galaxy. This is a sombrero galaxy, and many of the little points that you see here are globular clusters. So this is to remind us that the globular clusters are halo objects, and they orbit up in the halo of the galaxy, and they constitute a relatively small fraction of the light in the halo, like less than 1% or so. So most of the stars in the halo are in the field, and very few of them are the star clusters. Now, of course, we observe clusters of much lower mass and much younger ages, and here are some examples here, and these have interstellar medium associated with them, so they're relatively recently formed objects. And so we see clusters of a wide range of ages and a wide range of masses, and in a wide range of environments. This is a galaxy that played a bit of a role in what I'm about to say later. This is the galaxy M83. It's a big grand-design galaxy in the southern sky. It's about 5 million parsecs away, and it has numerous star clusters in it of a wide range of ages, and you'll see some data that relates, in fact, to this image from Hubble here later. This is the antennae galaxies, and just to remind you, these are two galaxies that are coming together probably for the first time, and they're about to merge or orbit maybe a couple times around each other, and then end up in one big elliptical galaxy when the whole thing is done. But for the moment, you still see the spiral structure in two. They're fairly ordinary galaxies. And these things are just full of young star clusters. In fact, it turns out that, and I think this was not a particularly expected benefit of the Hubble Space Telescope, was that it would be very, very good at studying populations of star clusters in nearby galaxies. One of the reasons people weren't sure about that is they didn't realize that the masses of star clusters, even young ones, extend up to fairly high masses. So one of the first discoveries of Hubble, when it was trained on interacting galaxies like this, was that there were relatively bright and blue point-like objects, but maybe not quite point objects. Objects which were so bright that they couldn't be individual stars for the colors that they have. In fact, if you took the colors and estimated the ages of the objects, you could then use the luminosity and a stellar population model to work out what the masses would be, and those turned out to be masses up to 1 million masses, in some cases more. So that introduced the idea that maybe we're seeing globular clusters in the process of formation in galaxies like this. And some of what I'm going to talk about today has a bearing on this question about how globular clusters are formed, what is a globular cluster, what's its relation to the young clusters we see nearby in our own galaxy, are there really distinctions between these kinds of objects, are they all kind of similar? So what I'm going to talk about now are some results from a series of studies that I've been doing over the last few years, partly observational and partly theoretical, and I've been doing it with these people here. For the observational part, my collaborators are with Polly Chandar and Brad Whitmore, and then for some of the theoretical work for the young star clusters, it's Mark Krumholtz and Chris Matzner, and then for some of the work on the evolution of the older clusters, Ian McLaughlin and Shane Zahn. So I won't be specifying exactly who did what in the rest of the talk, but these are the people. Okay, so how can we be a bit more scientific than just look at these pretty pictures and identify a few objects and give them some names or classifications like star clusters? In other words, can we go beyond sort of a botanical description of these objects? And that involves making measurements of the most salient features of the clusters, and then looking at the population of objects, making distribution functions for these properties. The two that are most relevant in the study that I'm going to talk about now are the masses and the ages of clusters. In principle, their clusters have more properties than just a mass and an age. They don't all have exactly the same internal structure. They don't all have exactly the same sizes. They don't all have exactly the same metallicity and cell population and so forth. But to a large extent, those are second-order corrections on the basic measurements of just how massive is the object, how many stars does it contain, and how old is it. And in fact, these other second-order properties are not accessible to us, even with the Hubble Space Telescope, for clusters more distant than a few megaparsecs. It's really difficult actually to see the internal structure of star clusters once they get to 10 megaparsecs and beyond. So the basic properties we're going to focus on mostly in this talk are the masses and the ages. And then we're going to do a census of the star clusters in different galaxies and different regions of galaxies, and look at the distributions of masses and ages. Let me just say a little bit about how we do that first. We have images of galaxies in several different wavebands, typically U, V, V, I, and H alpha. H alpha is very important because that's on when the cluster is younger than about 10 to the 7, and it's on when clusters are older than about 10 to the 7 years old. And then what we do is we fit a stellar population model to the measurements in these 4 or 5 different bands and arrive at a best fitting age and a best fitting reddening. And so once we have the reddening, we combine that with the luminosity to estimate the mass of the cluster. So in this way, for each cluster, we get an estimate of the mass and the age of the cluster. And this is just demonstrating how, if you were to vary the age of this, these are measurements of a particular cluster here in a particular galaxy. And if you were to take your model and vary the age, you would get a spectra that were different, especially this H alpha line here. And so you can do fitting and estimate a best fit age and reddening from that. Then you get the age and the mass. And here's another one just to show how this works for an older system here, but you can see that there's enough information with these 4 or 5 bands to determine a mass and an age independently reddening. Then what we can do is we can plot up the points, one for each cluster, in a diagram like this, which is the distribution of mass and age. This happens to be the distribution for the LMC clusters. And then we can count the clusters in various directions in this diagram here to form the age distribution. If we were to count this way, for example, at a fixed mass, or if we were to count this way, we get the mass function at that particular age there. So we form diagrams like this and then do the counts. Now, I'm skipping over a lot of details having to do with making sure the sample is complete and unbiased and things like that. That would be a talk in itself, but this is the basic idea, just to give you a feeling for how we do this. And here then are the results that come out. And what's plotted in this diagram here is the log of the number of clusters per unit mass. So this is the mass function plotted against the log of the mass for 6 different galaxies, 5 of which we've studied here using the techniques I'm describing, and one of which has to do with the clusters measured locally in the solar neighborhood in about 1 kiloparsec of the sun. And then the samples are further split down into different age bands here. And then the mass functions plotted, say in this case, for the clusters that are between 10 to the 6th and 10 to the 7th years here, between 10 to the 7th and 10 to the 8th years here, 10 to the 8th and 10 to the 9th years here, and so on and so forth for the different galaxies. So here's the antennae in M51. These are interacting galaxies. Here's the Milky Way and M83. Those are nice big ordinary spiral galaxies, and the LMC and the SEC, those are dwarf galaxies. And what's interesting is how similar all of these things are. How similar the mass functions of the clusters are from one galaxy to another, but also from one age to another within a given galaxy. So these lines are essentially parallel to each other here. When you fit the exponents, they come out to be roughly m to the minus 2. Well, the average is actually minus 1.9, And there's a dispersion about that. They don't all have exactly the same value. Within plus or minus about 0.2, that's our ability to make the measurement. So there may be minor differences from one galaxy to another, from one age to another. But to a first approximation, these things are all the same. There's some hidden underlying pattern here that we detected by making these distributions and plotting them up and comparing them this way. So I'm not saying they're all exactly the same. We have observational errors, but if there are differences, they're at or close to the level of the observational errors, namely the plus or minus 0.2 in the x component. Yeah.
Is the upper cutoff of the masses interesting, or is it probably just observational?
This, that you put your finger on a very good point. This is, as you can see here, we see a parallel up to the last point. And in general, the last point here is plotted in a beam that has only 2 clusters in it. So that's very suggestive that there is no real feature in the distribution at the end here. The next thing you can do actually is you can calculate, if you were to extrapolate this up to infinity, how many clusters would you expect to find under that distribution from 0 on up. And that's always 1, 2, 3, something like that. So we see no evidence at all for any feature in any of these distributions. And another corollary to that, of course, too, is that the brightest cluster you will see, the most massive cluster you will see, will be related to the size of the population. If you're in a galaxy that has 10 times as many clusters in it, then the upper mass that you find, it turns out with an n to the minus 2 power law, the mass function will be 10 times bigger. It goes linearly with the population size for an n to the minus 2 mass function. Okay, now we can do the same thing with a cut in the orthogonal direction in this mass age plane. And that gives you the age distribution in different mass inputs in different galaxies. And that's shown here. So again, the same galaxies plotted in the same order. We don't have the data here for M51 for various technical reasons. And again, the age distribution of the clusters showing something that can be described approximately as a power law, and with roughly the same power law index when the sample is subdivided into different mass intervals. So notice how parallel these lines look.
So is the y-axis and all these things, you have this constant there, is this all scale with like the star formation rate, the overall number?
Yes, exactly. And that's you put your finger on one of the main conclusions of all of this, is that there's just basically one number in the problem. Let me come back to that in a minute. It's related to the previous question too. But that's exactly right. So again, these functions, these mass functions are parallel to each other in different age intervals. Same parallels. And likewise for the age distributions. It's not quite as pretty in this case, and that there may be slightly bigger differences in the slope from one galaxy to another here than in the mass function. But to a first approximation, they all fall down as roughly age to the minus 1.8. That's the average, although there's a fluctuation around that at the level of 0.2. Again, very close to the observational errors in what we can do in this kind of work. So if these things are parallel to each other in different mass intervals, and the mass functions are parallel to each other in different age intervals, it means that the joint distribution is separable in these two verticals. So the joint distribution of masses and ages of all of these clusters, you can approximate as the product of two power laws. The index on the mass is about -2, and the index on the age is about -1. And there are no other features seen. Now we can't resolve features in these functions that are smaller than about 0.3 or 4, or in some cases even 5 gaps. So we have to take big bins to determine these functions. And there could be fine scale structure that we're missing, but to the extent that we're looking at the big picture here, And the general trends here, these distributions in these 6 different galaxies can be approximated by basically a joint distribution of masses and ages going up, mass to the -2, h to the -1. And then, as Shane just said, that means that there's only really one parameter of the problem, which is the up and down normalization. And that's got to be proportional to the overall size of the population, which in turn is proportional then to the formation rate or the total number of clusters, however you want to say it. So what I'm claiming here is actually the whole zoo, the whole botanical zoo of star clusters, to a first approximation can be boiled down to m to the -2, total -1, times a normalization that's actually not interesting. It's just proportional to how big the system is. And that for clusters up to about 10 to the 9th years, this is sort of the main part of the story here for star clusters. So we're using the word quasi-universal to describe this. I guess we're really ready to call it universal, but as I say, we think there may be differences, and we do expect physically that there should be differences at about this 0.2 level. So for some purposes, it's good enough just to think of all these populations as being basically the same. Now this holds for, I should say, for clusters up to about 10 to the 9th years old. These are valid in the range we've studied them, which is about 1 million years to 1 billion years in age, and in mass from about 100 solar masses up to 1 million solar masses. And in that range, in these 6 galaxies, very diverse, different kinds of galaxies, this is what we point out. Could be different in other places. You can imagine reasons that it might be and so forth. For example, a galaxy that has no recent star formation or cluster formation is not going to be describable this way. It's obviously going to have a very different age distribution. But for the galaxies that are churning away and making clusters for the first 10 to the 9th years in the life of the population, this seems to be a good description.
Can I ask a question about that? Your time dependence? So you said roughly goes like t to the -1, roughly. So that's equivalent to saying per logarithmic decade time, there's equal number of clusters being formed.
And in fact, this is the first thing I noticed actually when we started plotting diagrams like this up. This one doesn't show it quite as well, but if you just scan along this direction here, you see that in log space, it's roughly a flat distribution.
But that's sort of strange. That would say we are living in a special time, because we come to time from us, right?
We are living in a special time. The special time is that a cluster doesn't start being disrupted until it's born, which is now. And so you put your finger on a good point that I want to talk about now. This age distribution, so far I haven't said anything about the physics of how these things are made or destroyed or anything else, but it's important to keep in mind that almost all stars are born in a clustered way. It's essentially safe to say that from a practical point of view, all stars are born in star clusters. But if you look at all stars older than about 10 to the 9th years old around us in the Milky Way or in any other galaxy, essentially none of them, or a very, very small fraction of them are in star clusters. It's a very, very, very small minority. So, and this is essentially quantifying that every factor of 10 in age, you lose 90% of your 90% fewer clusters by the time you go up each factor of 10 in age, you go down a factor of 10 in the number of clusters. So what could be causing that? Well, in principle, this relation here reflects some combination of the formation rate of the clusters and the disruption rate of the clusters. Now we know from various studies measuring in detail the color of field stars and so forth very, very carefully in the Milky Way and the LMC and other nearby galaxies, that the star formation rate has changed over the last billion years, typically by factors of 2 or 3 or less. But the age distribution here has dropped down in all cases by not factors of 2 or 3, but by factors of 2 or 3 orders of magnitude. Okay, so it's it's virtually certain that what we're seeing here mostly is the disruption of the clusters. And in that sense, we do live at a special time. Everything is disrupted and gets more disrupted as time goes on from the time the clusters are born. So, and this, I believe, is what explains why these things are so similar from one to the other. Okay. Let me show you a really extreme case of that now. So, the first approximation, I believe most of this is disruption. There is a modulation of these age distributions by the formation, the history of formation of stars and clusters in the galaxy. But I believe it's at this sort of level here, close to the observational errors. It turns out the 0.2 error actually encompasses a factor of 2 or 3 change in the formation rate. And so we do expect real differences at the level of 0.2 or so in these exponents, just because we do know that the star formation histories have not all been flat and constant in all galaxies over the last 39 years. They vary by factors of 2 or 3. So some of this variation we're sure is real.
So my one is like
Yeah.
antennae, right, is currently undergoing.
Exactly.
So it's not obvious from its power lines.
I know, and that's what I want to say the next thing.
Can I ask a question?
Yeah.
Getting interrupted. It's
You're
interesting.
getting it.
So can you tell by looking at the young ones, you have enough information to tell which are going to be the survivors after 100 million years?
The quick answer is no. The quick answer is no, because for many of these galaxies, they're just too far away to see subtle differences within the clusters. But let me come back to that. There's a partial guess to that, but it'll be confusing if I say it now. Let me make 2 points here, and then I'll move on to the extent to enormous point. Sorry we can make 2 points before we get on to any of the interpretation of any of this. And one is the one I've already mentioned, which is that if we've doing this work, it's very labor intensive. Each of these galaxies is a study in itself. But if all the galaxies have mass functions of clusters that go like n to the minus 2, then as we discussed earlier, there's a relationship between the statistical relation between the brightest cluster and the star formation rate or the cluster population size that we ought to be able to verify. So this is a sort of a poor person's way of checking for consistency in this scheme for galaxies where we don't want to do all the laborious work of measuring all the masses and ages of all the clusters. We can be so lazy as just to measure the properties of the brightest one. That's easy to pick out. So that's what's done here. This is the luminosity of the brightest cluster versus the size of the population of clusters, which is proportional to the formation rate. And this is the expected behavior if the underlying mass function is just a power law in mass, and it's independent of age, and goes like m to the minus 2. In that case, the luminosity function also goes like L to the minus 2. And you get that this is basically 1 power luminosity here. 1 power, the luminosity, expected luminosity, goes to the first power of the population size. And that's actually not too bad. There's some dispersion around that, and whether that's real or not, I'm not sure. Probably some of it is. But anyway, it's close to being correct. Then there's one other hobby horse that I just want to saw briefly, and that is those of us who learned about star clusters in our early astronomy classes, learned about all these different things like associations and open clusters and globular clusters and cosmos and so on and so forth. And what I think this work says is that that's, like many of the things, notation and nomenclature that astronomy comes up with, astronomers seem to be uniquely able to find unhelpful nomenclature and notation. And this is a perfect example of this because, if these functions had features in them, like this, they went like that, and had multiple modes, you could say this is the open clusters, this is globular, and so on and so forth. That would make sense. But clearly with power laws, it means any separation of clusters by type, right, by some sort of naming convention. It has to be only that, just a convention, basically an arbitrary decision to say that things older than this or younger than that have one name or another. There's no physical basis for that. Okay.
Wait, here's a question. If you don't have globular clusters on there, maybe.
I'm coming to
You said that they're
globulars.
running in billion.
Yeah, for now we're talking about billion. I'm coming to those later. They part
But
of
these usually are part of your second statement.
Yep, but you'll see how that this is still true about them just in a little bit later. Okay, now to normal stuff. Here are the antennae. This is the real antennae, a real image of the antennae taking the bubble. But many people have simulated the antennae, basically by doing n-body simulations, including gas and star formation, and so on and so forth. There are about 6 or 8 published simulations of the antennae. And you could worry, as Norm just did, that with the antennae you are seeing a burst of cluster formation recently, and that might be partially the explanation for the fall off in the age distribution. And that may be true, but what I'm going to try to convince you of is that it's a very small part. This is the history of the star formation versus time in all the simulations, published simulations of the antennae. They all have different recipes, they have different orbits. Don't worry about that. They give very different answers, and so you shouldn't believe any of these. These are all trying to simulate. They're all trying to simulate this picture here, and they've all been plotted in the same way, normalized so that this 0 in time is supposed to be when we're looking at the simulations now, and this is the history of star formation in them. And sure enough, you see, look at this. You see this. This is just what we were talking about. These large jumps and so forth. So shouldn't this be reflected in the age distribution of the clusters? Well, if we replot those log way, the same way as the observations, and normalize them all at the young age here, these are all the same star formation histories here. And this is the observed age distribution clusters in the antennae. So you see that this is actually quite flat here, out to a few times 10 to the 8 years, and maybe even beyond, maybe even all the way to 10 to the 9 years. And certainly there's a divergence between the observed age distribution clusters of the antennae and the star. Now we don't know what the real star formation history of the antennae is, because it would be too hard to determine the ages with lots of individual stars. So this is as close as we're going to get for a long, long time. But we can now take this star formation history here and put in a power law disruption rate. We can say that the survival probability goes down as a power law of age, like the one that we see in more normal galaxies like the Milky Way and M83, and then we essentially convolve that power law 1 over age with this, and then replot. And this is what you get. It's a fantastic thing. So, as far as we can tell, everything in the antennae are also consistent with this basic story. The fact that there are differences in the star formation history come in at a level that's not terribly important in these kinds of considerations. They're there, but it's not the dominant thing. Okay, so this is the empirical story. Now let's see if we can figure out what it means. So the clusters are born in molecular clouds, and not just anywhere in the molecular clouds. The clusters tend to be born in the densest parts of molecular clouds, the so-called clumps. And it's been known for a long time that the mass function of molecular clouds is a power law with an index about -1.8 here. This is looking at objects whose densities are bigger than about 100. And this is an attempt to measure the mass function of the clumps within the clouds. And it has a slope of about -1.7. So suggesting some kind of self-similarity on different scales within the clouds. But anyway, these are close to the kinds of power law indices that we've been seeing. They're actually a little bit closer than these numbers would suggest. If you allow for the possibility that more massive clusters, which have longer turnover times, and therefore probably longer lifetimes, if you take that into account, that any given sample, the more massive clusters will be seen for a bit longer than the low mass clusters, and you fold that in, that actually takes the power law like this and converts it to n to the -2 for the initial birth rate mass function for the clouds and bumps. There's about 0.3 in the exponent difference between the birth rate and the instantaneously observed rate if the clouds are living a lifetime that's proportional to their internal dynamic time, some multiple of the internal dynamic time. That all makes sense. So that means that the clusters from which the clouds form have a mass function that's very similar in shape to the mass function of the clouds or clubs. And you could say, well, so what? How could be anything different from that? And that would be true if all of the gas in the protocluster turned itself into stars. Then obviously, the protocluster mass function would be the cluster mass function, maybe, if there were no change in mass. But we know actually that a rather small fraction of the ISM in the protocluster gets turned into stars. So at least in principle, what we have to understand, the fact that this slope, when corrected for this lifetime effect is essentially the same as the cluster slope, but the efficiency, the overall efficiency of star formation is not 1, it's some number quite a bit lower than that. That means that the efficiency has to be mass independent. That's the only way you can preserve the shape of these mass functions. So then the question is, how do we understand why the efficiency is a constant, or roughly constant, independent of mass? And let me go through a little argument there. So what we're finding now is, just to summarize, is that the mass function of the protoclusters, the primarily gas-dominated protoclusters, to the young clusters, stellar objects, to the somewhat older clusters and older, and so on up to about 10 to the 9th years, keeps the shape of the mass function, but it's always going down. You start with the cloud mass function, you go down by a factor of 10 or maybe a little bit less, 5 to the initial cluster mass function, and then about a factor of 10 for each factor of 10 and 8, but not changing the shape. So, but we've said that this dropping down of the mass function of the clusters has to be because they're being destroyed over time. And that means that the destruction mechanisms also must be independent of mass. So that the probability of a million solar mass cluster surviving to 10 to the 9th years has to be the same as 1,000 solar mass cluster. This, I think, came as a surprise to many people. There was a photo on the subject before we started doing this work that said that the more massive clusters would be more robust. They should be able to withstand most of the destructive effects, be hardier, and I think more of those would last. And so that the mass function would probably be tilting and becoming flatter with time, but it doesn't do that. So let me talk a little bit about some of the physical reasons why that may be. We have to now talk about the various effects that would destroy clusters, or in the initial case, expel gas from the clusters and reduce the star formation efficiency to some number like 20% or something like that. And then we have to understand why these are independent of mass. So the first disruption effect that the cluster has to withstand to survive is the feedback, the fact that there is energy and momentum input into the ISM in the cluster. And if this is removed from the cluster, the binding energy of the cluster is reduced, and in some circumstances it can stay together as a bound object and it will be dispersed that way. Then, after that happens, and that goes on up until about 10 to the 7th year, the cluster is about 10 to the 7th years old, the stars in the cluster, even though it's an entirely stellar system, they're still continuing to lose mass. And which, for an isolated cluster, wouldn't do you any good, but for a weakly bound cluster in a tidal field, it turns out even a very small amount of mass can cause the cluster to fail to find a virial equilibrium point, and so it can be destroyed that way. Even 10% mass loss can be important if the cluster is weakly bound and in a tidal field. That's the second. And then the third important mechanism has to do with the fact that the clusters, when they're in the disk of the galaxy, they find molecular clouds, which are perturbations to the gravitational field that they feel going by them. And these, when they go by fast enough, can induce an impulse into the orbital motion of the stars within the cluster, which it can't respond to quickly enough as the perturber goes by. And that introduces an extra random motion for the stars within a cluster. And over time, more and more of these things will cause the random motions within the cluster to increase. Its binding will become weaker, and the thing can be dissolved that way. So those are the three candidates for essentially disrupting the clusters from the time they're born up until about 10 to the 9 years. I'll talk about some other effects that take over from 10 to the 9 years up to a Hubble age in a minute. But these are the ones we have to consider in the age range that I'm talking about here, up to 10 to 9 years. And the question is there any mass dependence in these effects? And let me just go through this quickly. In the case of the removal of ISM, you can do a little back of the envelope argument. Well, let me back up. There are many processes that inject energy and momentum into a protocluster. It could be from the protostellar outflows. There are eventually supernovae. There's a radiation from the young stars pushing on dust grains, which coupled to the ISM through magnetic fields can drag the ISM out. There are winds from the main sequence stars, which blow bubbles and can eventually expand and carry material out with them. And then just the photoionization of gas as the region becomes an H2 region and fills itself with ionized gas, that will increase the velocity dispersion, and if that's higher than the escape speed from the protocluster, then it will be dispersed that way. So it's a complicated business. There are all these different things going on. It's a very fascinating study to try and understand all of this. We've been trying to do a little bit of this. Somebody who's done a lot more of this is Norm, and some of the work that we've been doing has paralleled his. It's an interesting subject, and it's not a settled subject. But you can treat the problem in two limiting cases. One of the reasons it's not simple to solve is because even if you knew which were the most important feedback effects and treated them correctly, the rate at which energy is retained in this proto-cluster object will depend on how rapidly it's rotating, which depends a lot on the internal structure, density structure within the cloud and so forth. But brushing all of that aside, you can do two limiting cases, which probably bracket most of the cases that are of interest. One in which essentially none of the energy gets radiated away. That's obviously way too optimistic in many cases, but it's a limiting case. Another case in which essentially all the energy that can be radiated away, the system is so dense it radiates away all the energy it can, and the only thing that does you any good is the momentum coming off the stars and pushing on the ISM within the protocluster. Anyway, you can do on the back of an envelope a little scaling argument to ask how much momentum and how much energy would I have to put in, energy in one case, momentum in another case, would I have to put into this cluster essentially to accelerate the material up to the escape speed of the protocluster. If I still kept on forming stars after that, or I couldn't keep on forming stars after that. So there's a certain critical star formation rate, a certain critical amount of star formation that would take place up to that point, which would just lift this ISM out of the protocluster. And anything beyond that wouldn't do anything because the stars would be pushing on a vacuum. That then will give you, up to factors of order unity, an expression for the efficiency of star formation just required to satisfy that criterion. It will be different in the energy-driven case from the momentum-driven case. And if you ignore all the details and assume that these things just scale up with each other in terms of the overall mass, then you get these two expressions here. That's a very simple calculation. Anyone here can do it on a matter of envelope. In the two limiting cases for the star formation efficiency at which the material would all be removed and star formation would cease. And they involve, the only thing they involve is the relationship between the masses and the radii of the protoclusters, because that determines the relationship between the mass of the cluster and its escape speed. And it's the escape speed that you have to accelerate this material up to. So this now is the relationship between radius and mass for cluster-forming clumps, molecular clumps, in the Milky Way, done by 3 different surveys. And it's the function here, you can approximate it by a power law, goes roughly as r to the 1/2. And you can then put that 1/2 back into these expressions here, and you see that this is essentially the case for r to the 1/2. This is the case of clusters having constant average surface density. And in that case, the efficiency of star formation is essentially the momentum-driven limit is independent of mass. And that was the thing we were trying to explain. It's not exactly independent of mass in the energy-driven limit, but if you put in alpha equals 1/2 here, and just do the math, you find it's a very slow function here. It's epsilon weight is mass to the 1/4 power. So these arguments suggest that the efficiency of star formation in the 2 limiting cases, and therefore one presumes in all the cases in between, will be a very slow function of mass. And if that holds up to more careful scrutiny and more exact calculations, then this is an explanation of why the mass function of the clusters and the protoclusters have the same power law shape. There's another question that somebody should try to answer now, which is why do the clumps have a mass function that's n to the -2, a birth function that's n to the -2, or mass function that's n to the -7. That has something to do with the turbulence of the interstellar medium and how that's built up and so forth and so on. As far as I understand, that's not a solved problem.
So on the off basis of the observations, can you tell the difference between them and the 0 and 1? Do they favor one or the other? The constant efficiency versus
That
peak efficiency?
0.25 is very close to that 0.2, and it's not about earlier. So it's for, I wouldn't want to push it. And even this has a little bit, even this alpha is uncertain by a little bit. So in principle, if you were sure that alpha is 1/2, and there are theoretical reasons why that's preferred actually. If you were sure that that was true, and if you were sure that the mass functions were similar over a wide range of masses, then you probably would favor this momentum-driven one. This is actually the one I think you would expect ahead of time anyway, because we're talking about star formation in these very, very dense regions. We did a little calculation. We tried to estimate what would be the effect of all the different feedback mechanisms. And for most parts of the M mass radius diagram for clusters, the momentum-driven processes did dominate. So there is a consistent story here that it's mostly momentum-driven in these very dense massive cloud, and that's consistent with this and with this little scaling argument. Okay. Now we've got clusters. They're very young, and they not all of them, but some of them survive this process of star formation. What happens next? Well, for most of them, the gravitational potential binding energy of clusters would have been reduced by the loss of some of their ISM. So you can expect that this population of newly formed clusters is going to be skewed toward objects which have a very low binding energy per unit mass. Or another way to express that is in terms of the central concentration of clusters. And n-body experiments have shown that clusters with very low concentrations actually do dissolve even with a very small bit of mass loss. So if you put a cluster that has a low concentration in a tidal field and dribble material out of the stars gradually, you lose only even 10, 20, 30%. You can unbind, the cluster goes unstable and disappears. So that's another mechanism that would continue to disrupt clusters on past this initial 10 to 7 years when the loss of the ISM is the most important thing. And here now we get to this question about the internal structure of the clusters. These are the measurements of the concentration of clusters in the LMC, and this is a very difficult observation to do. Anyway, this is essentially the log of the ratio of the core radius to the tidal radius, which tells you how deep the central potential of the cluster is, and therefore how resistant it's going to be to disruption by this mechanism, and plotted against the log of mass. And these are difficult measurements to make, and these are the only existing ones. And this is not a complete sample of LSD. This is just all the ones that have been observed and studied this way with HST. And you see here concentration is independent of mass. And that's what you need for this mechanism to have a disruption probability independent of mass. So you would need to do a more detailed calculation to calculate how many clusters are lost during the time and that sort of thing. The measurements are not good enough for you to put in such a calculation if you did it, but you would at least, you do want to check that the concentration of clusters is independent of mass. So that's at least consistent with the fact that we see the mass functions remaining parallel from 10 to the 7th, 10 to the 8th years. Now after 10 to the 8th years, the most important disruption effect is these encounters with molecular clouds. And let me just say quickly that this is a well-understood process. You can look up the convenient domain, vectorial formula taken from convenient domain. This is the disruption timescale expressed in terms of the density of the clusters, and then things that depend on the number of perturbers, on the mass of the perturbers, the molecular clouds that are running around and disrupting these things. But the only dependence on the properties of the clusters is through their characteristic internal density, rho. Okay? When the disruption is mainly because the cluster is destroyed by a single catastrophic encounter, this formula applies. When it happens in a different regime, for clusters that are smaller, then the main effect is the cumulative effect of lots of weak encounters over time, building up the internal energy of the cluster and destroying it that way. This is this diffusive regime. And there's a different dependence on rho, the internal density plus rho H in these two cases. But rho is still the only variable that the thing depends on. And so you want to look at what the density of the clusters is versus their masses. And again, this is the same LHC sample and no correlation here. So that's what you want to see in order to understand why the disruption probability or rate and so forth is independent of mass, keeping the mass function parallel to itself as time goes on.
This gives you some idea of the scale of the response because it says that the positive again, third of the problem.
Sorry?
This says that in clusters it's different than in clumps, I guess. Because it says that R doesn't end in 1/3, but it's 1/2.
If this were exactly flat like that, then yes. And in fact, after this talk, I'll show you a plot that shows the actual radians versus minimums. And it actually has the best enhancement that's about 1/3. But again, the 1 sigma uncertainties are enough to get you to a half. So I wouldn't want to, so yes, the two studies that we've done to look at mass versus radius for clusters and clumps have best fitting exponents that are slightly different from each other. Whether they're truly different from each other, I wouldn't want to risk very much.
Is the destruction of cluster driven by internal dynamics of the cluster or due to the internal interaction with the galactic field?
This is mainly from the fact that here's a cluster, and here's a molecular cloud, and it goes by. And so the stars that are orbiting in this cluster, they feel a time-dependent potential. And if the molecular clouds go by, this is the perturber of the molecular cloud. If it goes by fast enough, while time scale short compared to the orbital period here, then the change in the motion of the stars is impulsive. And it doesn't go, it's a net input of energy into the cluster, which comes from the relative orbit of the cluster and the clouds. Okay? So it's tidal perturbations, basically, and lots of them. And in one regime, if you have a big puffy cluster, a molecular cloud can go right into the center and blow the thing up on a single encounter. That's the catastrophic regime. If the cluster itself is very tightly bound, then you've got to have a lot more of these things pass by outside, and then the effect builds up, and that's the diffusion.
I mean, for Lomas cluster perspective, just internal dynamics will lead to evaporation, right?
Well, you're probably thinking of relaxation effects, and that's going to come in just a minute. That will be important for very, very low mass clusters that would be important in the regime we're looking at. It turns out, for the clusters in the mass range that I'm talking about here, and the age range of a billion years, internal relaxation alone will not cause much disruption. But we'll highlight that in just a minute when we come to the body. Okay? So these are the disruption mechanisms that are... Okay, so let me just summarize the results for the young clusters. We've seen that the mass function is similar to that of one for clouds and clumps. It's similar from one galaxy to another. It's similar from one age to another. This is basically a recipe. This is a rule. This is some regularity in the way stars form in galaxies. We're used to thinking of trying to understand the stellar initial mass function, why it has a saltpeter, high mass, slope, and so on and so forth. I would actually put these results sort of on a par with that, because this is some basic feature of star formation that we've now seen in these three galaxies. We don't quite understand why it's the way it is, but the observational evidence is pretty compelling that we are seeing similarities. It's the same way with the saltpeter IMF. If you could actually sit down and try and think about how stars form, you would never, I think, arrive at the idea that the mass function of stars should be the same in all environments and different metallics, and on and on and on. There are just too many reasons why it could be different. And I think we're seeing it for reasons which we don't fully understand. We must be seeing something analogous to that here as well, except that it's also a similarity in the age distribution, not just the mass function, but also the age distribution. So I think there's an analogy here between the regularity we see in the mass function for stars and for clusters, and the kinds of thinking that will be required to understand all that. And I see that I'm about to finish here, but let me just make one quick point. I've got us up to 10 to the 9th years. So one more decade in age, 10 to the 9th to 10 to the 10th years. And because the question came up, so could I just take a few minutes here to talk about that? If you look at the mass function for clusters younger than a giga-year, specifically younger than 10 to the 8 years, there are these power laws that we've been talking about up to now. On the other hand, if you plot them in the same way, this is the log of the number of clusters per unit log mass now, per unit log mass, then this is still a power law is a power law, no matter how many logarithms you do here. The mass function for the old clusters, the so-called logar clusters, in the Milky Way and the Sombrero, are functions that are peaked here. So in this case, something has happened. If these objects are the progenitors of these, and that's an if, but if that's true, we should at least entertain that, because we know galaxies are making clusters up to the masses of logar clusters. So wouldn't it be cool if we could make our young clusters this way with power law mass functions, and then put them, in a merger or whatever, put them up in the halo galaxies, and let nature take its course somehow and end up with the logar cluster mass. We have to figure that out if these things are related to each other. Okay? And I don't have time to go into this, but there's a very pretty calculation which allows you to calculate how a cluster of a given mass in a tidal field loses mass linearly as a function of time. M dot is a constant. And if you put that in as an initial value problem, this is your initial mass function, and turn the crank up to 12 giga-years with no free parameters. And again, this is something I realized after the fact you could do on the back of an envelope. Let me just, I have to skip over this. And anyone who wants to see this, I'll talk to you later. That's quite pretty. And I think I did talk about it once when I was here before. But anyway, if you do this calculation, which is essentially analytical calculation you can do on the back of an envelope, taking into account this loss of stars by relaxation. The way this works is that because of the scattering of stars against each other when they orbit around in a star cluster, they're doing this at all different angles and so forth. They are trying to reach a state of thermodynamic equilibrium. They're trying to reach some sort of Maxwellian distribution. Maxwellian distribution has a tail of velocities that goes up to infinite velocities, but the cluster itself has a finite escape speed. It's basically the square root of 2 times the velocity dispersed. So that means that the scattering of the stars is always trying to send some stars up into this tail, but the tail gets ripped off. Every time they get up above the escape speed, they're gone. So there's a diffusion of stars out of the cluster, and the final result solved is just a tight binary that's left, and everybody else is offered infinity. It turns out if you do that process, that relaxation, two-body relaxation process, in a tidal field, clusters lose mass at a rate that's approximately constant that depends only on the tidal field strength of the galaxy. And if you then evolve an initial function like this, which we take as the function of 10 to the 9th here, say, and you just evolve it, this is what it looks like at, this is at 1.5 years, this is a t equals 0, 1.5 years, 3 years, I'm going to 6 and 12 gigayears, and these are the observations, there are no free parameters. So anyway, this is the point that when you talk about the globular clusters, they do have a feature. For these old objects, they do have a feature in their mass. It's just a little bit above 10 solar masses. But that is what you would get for free by starting with the power law, initial mass function for 10 to the 9 years, and just letting nature take its course. It will give you this. It will give you the mass function of old globular clusters. So there's a story here that basically says the two things you got to know about star clusters. One is for clusters younger than 10 to the 9 years, m to the -2, total -1. That's about all you have to know about star clusters. And then for clusters older than that, they lose mass at a constant rate. And this mass function you can write is equal to this mass function where the argument is m times the escape rate times t. You just write one little equation. And that's what you need to know about star clusters. Okay?
Thank you, Mike. And do you have any further questions?
So you said this is analogous to the self-return initial mass function. But surely you also use constant initial mass function for your differences. Did that have to some?
No, well, okay, that's a good question. Let me answer. It's got a simple answer. Let me go back here. You would worry that maybe these diagrams here are influenced by the fact that we've estimated the masses and ages of each cluster with a style population model that has an assumed element, which may or may not be. Now, the one we've assumed, of course, is the solar neighborhood IMF, the group or whatever you want. But the colors of the star cluster of stellar population are determined primarily by the color and the mass of the stars that are just turning off the main sequence, because most of the light is coming from these stars near the main sequence turn off, and the giants that have taken off after that, but they have all about the same mass. So essentially the color of a cluster is determined by stars in a very narrow range of mass. Therefore, the color is very insensitive to the IMF slope. What is sensitive to the IMF slope is the so the shape of M on L. Essentially what we do is we take the mass to light ratio of the models and multiply them times the light of the cluster to get an estimate of the mass of the cluster. Now, so I just said that the shape of the mass to light ratio versus age is essentially independent in the first approximation of the IMF slope and shape. But its overall up and down does depend on, for example, how many low mass stars you have, because they don't contribute anything to the light, so they don't contribute anything to what we're measuring when we're making a diagram like this. So the scale, all of the scale this way, could shift a little bit by factors of 2 or so. But look how this is a whole order of magnitude. A factor of 2 is, I don't know if you can even see it from back here. So going from the saltpeter IMF, which is power all the way down, versus the cripple, which turns over and flattens, that would actually change, all these points would move over by something I don't think you could even see from back there.
I think one more question.
You mentioned earlier that this applies to galaxies with high star formation, so you have a rough estimate of the minimum star formation rate?
I'm sorry, I didn't hear you.
You mentioned earlier that these mass functions and age functions apply to galaxies that have a certain star formation rate. So is there a minimum cutoff star formation rate that you can estimate?
No, what I think this would be fine even if you dial the star formation way up or way down from what we observed here. What wouldn't be fine is if, let's say, you stopped all star formation 10 to the 8 years ago, then there wouldn't be any clusters. There wouldn't be any clusters from here on over, so the function would go up and then it died down with that. So if you had no recent formation, let's say you haven't had any formation of clusters, let's say up till a few gigayears ago, for some reason you had a merger and all of that stopped, then the youngest clusters you would see would be whatever the age was of the merger. You wouldn't see any clusters younger than that. But the arguments I gave you about the globular cluster mass function would still be in effect. So they would still explain why globular, you would see old clusters in the merger method, and the really old ones you would call globular clusters, and they would be fitted by this mass function.
I think, Mike, as we move up, another discussion.